Carlo Rivelli, welcome to Within Reason.
Thank you very much. Pleasure being here.
I should tell our viewers that this is the second time we've tried to do this, and there's an irony lurking in there somewhere. You're the author of The Order of Time, and I wanted to talk to you today about the philosophy of time. One of the most interesting things that you bring people's attention to is the fact that well, as I put it in an email to you, your time is not my time. We tried to record this before, and I'd mistaken the time zones, and so you were ready an hour before I was, and it was all a bit messed up, and we had to reschedule. And in my apology to you, I said, "Look, I'm so sorry. These time zone mistakes do happen. After all, your time is not my time." So I suppose I should begin by asking.
That's right. We're not in the same time.
Yeah. Do you think that I can be blamed for being unintentionally late for an interview if time, in fact, does not exist in the people think in the way that people think it does?
Nice question. Well, there is a subtle relation between the difference of time due to the time zones and the difference in times due to relativity effects. These are two different things, right? We're talking about two different things. But nowadays, we easily get confused about the relativity of the relativistic effect of time, and only once in a while, like as we did, we get confused. We get confused about time zones. But there was a time in which time zones were extremely confusing for people. People just didn't understand it. The first time the boat of Vasco da Gama did the tour of the Earth, it came back, and then there was a huge dispute about the number of days it took, because of course the number of days, if you stay put in London between departure and arrival of the boat, is different than the number of days that the boat that goes around the planet experiences. The difference of one. You think for a moment, it's pretty obvious, but everybody was confused at the time because people were very much confused about time zones. You see, time seems completely intuitive and simple, but is not.
Yeah, I mean, that's a fascinating place to start, this issue of traveling around the world. And of course, as the Earth rotates, if you circuit the Earth and come back to where you started, it seems, at least experientially, a different amount of time has passed for you than somebody else. Is there a way of trying to work out an answer to this question? That is, if I were to ask, when one person says it's been 2 days and one person says it's been 1 day, is there a way for us to find out who's correct on this issue?
No, that's the point. They're both correct. So if you, I'm in Canada right now. So actually I'm in London, but the different London in Ontario, London in Canada. So if you start from London, UK, and come here, then when it's sunset here and it's time to go to sleep, your day has been longer, right? Because of jet lag, and for you it's deep in the night, and you go to sleep later. And if you keep going a little bit more west, your day is still longer. If you go still more, your day is still longer. Once you come back in London, you have had a number of days which are longer. So that means that you had less days than your family who stayed put in London. All right, so now you can put who's right, who's wrong in counting days. Well, depend on what you mean. If you mean the number of sunsets you have experienced, your days are less. If you need the number of sunsets the people in London, UK have experienced, they're right. So it's a matter of how do you want to define the days. And for the relativistic effects, which have nothing to do with the jet lag and the time zones, is something similar. If you and I match our watches, and I go for a fast streak and come back, then I have experienced less time than you. Now, who's right? Nobody. There's no universal time. There is a time for each one of us. Each one of us is in its own time, depending on where we are, how we move, and we can send signals, we can talk, we can meet, but we cannot have a global timekeeping. That doesn't work.
Yeah, I want to talk about these relativistic effects of time. The time zones thing is an interesting way to get started thinking about the concept of time moving differently and in a more intuitive sense. But the most groundbreaking implications of relativity, to me at least, as a layman who knows just as much as the next man about these theories, is its implications for time. I want to, most of my listeners will probably be aware of this, but just to spell it out, when you say that there is no universal time, what exactly do you mean?
It means the following, that if we hope to have clocks for all of us, so to say, that remain synchronized, that indicate all the same time, we just fail, because there is actually a different amount of time passing in different positions, and for people moving in different ways. So the very notion of a single time for everybody, it's wrong. Actually, let me backstep just a little bit, because once again, the time zones and the relativistic effects are more connected than one can imagine. Historically, for the following reason, the guy who first realized the complexity of relativistic time is, of course, Albert Einstein, who came out with precise equations for describing how clocks move differently depending where they are and how they move. And this was a little bit more than a century ago, 1905, when he wrote the paper. And at the time, it was just a theoretical idea by him. Today, it's an experimental fact. It's something that we can measure even in a laboratory. In a laboratory, if you take two clocks, two equal clocks, completely equal, which indicate the same time, and you move one a little bit higher than the other one, just a little bit, and wait for a little bit, and then come back and compare the two clocks, they indicate different times. The one that has been higher indicate less time, and the one that is lower indicate more time. So literally, there is less time on your head than on your feet. When you grow old, your feet age more than your head, unless you live upside down. Because what's happening is that the Earth, the mass of the Earth, slows down the passage of time. Now, all this we can measure. All this was understood by Einstein in 1905. And the cute thing, the surprising thing, is Einstein at the time was not a university professor. He had studied and graduated in physics, was a very good student in physics in Switzerland, but then he couldn't find a job. So he was hired famously by the patent office as a clerk in Bern, in Switzerland. And he was spending his time by checking patents for various technological projects. That was the beginning of the 20th century. There was a lot of technology developing, and in particular, there were the trains. Trains were becoming common. Just began the train stations. So there were all these railways across Europe, and there was a problem of keeping time for the full railway system. So you wanted every train station in France and Germany and the UK. UK, there was no tunnel under the channel. But in Europe, there were this connected train station, and you wanted all the clocks in the train station to synchronize. And that's not trivial, because at the time, still, people used to synchronize the clocks in every village using the sun. So you would put 12 o'clock, noon, when the sun passes over you. That is the best way to synchronize time locally, to arrange your clock. So everybody in the village has the same the same time, and you have a church usually in Europe, and on top of the church there is a sundial which tells when exactly every day you can check that everybody's at 12 o'clock, which is great for the village, but it's not great for the next village, because if you go a little bit east or a little bit west, the sun passes on the zenith a little bit before, a little bit late. So at the time, there were no time zones. Every village have a different time zone moving east and ovest. So Berlin and Paris were about 1 hour apart, but even Paris and Bordeaux were 15 minutes apart. Okay, so it was a hell of a problem now for time for trains, because good luck to write the schedule of the trains if every village has a different time. So the problem was let's synchronize all the clocks and find a common time. But then you have to synchronize. How do you synchronize the clock? You have to send a signal, but the signal takes time. So there were a lot of projects that Einstein was evaluating about the problem of synchronizing clocks in the train stations. Okay, and of course there's a simple way. You just send signals. You have a central point. You send signals everywhere. The signals are fast enough that this works. But Einstein knew that fast enough doesn't mean infinitely fast, because light takes time to travel. So he asked the question, wait a moment, if I remember that light takes time to travel, and if I know how light moves, because we know the Einstein equation, the Maxwell equation, and this and this and that, can we really synchronize clocks? And astonishingly, he came to the conclusion that we cannot.
Interesting thing to me is that it's such a radical and unintuitive conclusion that time is not absolute. And yet there's a sense in which people understood this intuitively from their everyday experience for thousands of years. The idea that, well, now for me is not now for someone in Paris, because the sun is in a different place. Midday for me is not midday for them. I mean, somebody in Australia right now isn't in the same time as me when I think about it in terms of the day. And there was a time when, how else would you determine the time other than what time of day it is? What other need would you have for judging the passing of time? And so the idea that my time might be different for somebody else's, as well as the idea that time doesn't travel at a constant rate. I mean, people always talk about how if you're bored, time travels faster. If you're having a good time, it travels slower, or rather vice versa. The other way around, I mean to say. And yet, although these intuitions were proved right in a way, they were proved right in a completely different way to how anybody would expect. I'm fascinated in this concept of time moving differently, like for your head rather than your feet, because the question that I have is, like, we often visualize this as you hold one clock above your head and you hold one clock down below, and when you bring them back together again, if you can measure them precisely enough, they'll have moved at different speeds. But surely even just the clock itself that you're holding up, the top of the clock would move at a different rate to the bottom of the clock, and the top of the second hand would move at a different rate from the bottom of the second hand. I guess that would equal out as it goes around the face. But I suppose what I'm asking is, so what's the minimum resolution here? I mean, is there a point that we get to where we can say that the effect of time is non-existent, or so negligible that it would never come into that we'd never be able to observe it, or something like that? In other words, if I'm imagining 2 points and time moving differently for those 2 points, do I actually have to imagine 2 literal points? Or can I imagine 2 objects that are small enough that we can say that time acts uniformly on the object as long as it is small enough?
You're posing a very good question, and this question has to do with taking things very small, right? And looking in the... And this is a question that has been a debate has come out very much in modern physics, because of the combination of the strangeness of time that Einstein clearly understood, and quantum physics. So once you bring quantum physics in, you find out that there is a minimum size of things. It's very, very small, but it's the minimum size of things. And therefore, there's no continuous space. The continuous space, it's an illusion. We better think at reality as little points, a granular structure of space. So you cannot go smaller than something. Now, it's very small, so for our intuition, it's just a point, because it's extremely small. But there is a limit. There is a minimum size you can go in saying where you are. There's no notion of where you are smaller than something. The continuity of space, the possibility of dividing space ad infinitum, smaller and smaller forever, it's a mathematical idealization. It's not true. That's not how the space is. So you're right in posing the question, and the answer is no. There is a minimum interval after which makes no sense to say where you are or how much time has passed. In fact, this is what quantum gravity, the physics on which I work, indicates, that there's nothing really continuous in the world. There is discreteness. There is a granularity all the way down. To go back to your, you were saying, it's very strange, this distortion of time, but after all, we knew about the distortion of time in another sense, right? You were saying, I mean, I get bored and half an hour lasts forever. I'm super excited, happy, skiing, and half an hour, oh boy, it's just so fast, gone. Of course, this directly has nothing to do with a distortion of time, the relativistic distortion of time. It's just a psychological effect. But we should see this the other way around, I believe. Namely, we know that our psychological time is it's flexible, is elastic. It's sometimes time goes faster, sometimes goes slower. Then we go to school, and we are taught, no, time is the same. We have clocks, all the clocks can go at the same speed. So we are taught, we are told, presumably as kids already, that there is this common universal time. But if we think for a moment, it's really a modern idea. It's not something intuitive. It's something that it became common in our culture. After Newton, after the scientific revolution, after the technological world, when everybody has clocks, when nobody had clocks, which is not long ago. Our grandfather probably didn't have clocks. There was this thing on some big clocks on the towers of the churches, which were all different from different villages and didn't work very well. And before that, which is they started in the 14th, 15th century, maybe in the UK a little bit later. Before that, people were just going with a sunset and sunrise and sunset. For instance, for many centuries in Europe, the day was divided in hours, but hours, there were 12 hours between sunrise and sunset, which means that winter hour were much shorter than summer hours. The measure of time itself was, flexible in terms of what a modern clock would say. So what I'm saying is that the flexibility of time is not so counterintuitive if we think about our direct experience. Then we learn a picture of the world, which is a Newtonian picture, which works very well, saying, look, we can think that there's a flat space all over, common time for everybody. It's a good way of thinking the world, but it's not a perfect way of thinking the world. It's not really very good. There's a better one in which we actually realize that time is not so uniform after all.
I mean, I struggle to think about the concept of time in my head. Right? Einstein shows us that time is a dimension, and it's sort of tacked onto space and you get space time, and you imagine the dimensions of space, and I can kind of point them out to you. I can say, well, look left to right now. That's one dimension. Look up and down. That's another. Look at the depth as my finger comes towards you. That's a third. But if I wanted to demonstrate time in the same way, I wanted to say, well, there's also this thing called time that exists. How do I demonstrate that to you? I say, well, close your eyes and just take note of the fact that now is not the same as a few seconds ago, and try to notice the difference. Try to realize how you can remember things that are not, in a way that you can't remember things that are coming in the future. In other words, I'd basically be asking you to start meditating if I even wanted you to begin understanding what time actually is. And even then, it's an incredibly difficult thing to picture. How should we be picturing time? What is this time stuff? Does time pass? Do we pass through time? I mean, what is actually going on here?
Well, first of all, picturing is easier than you say. And in fact, if you go to school in a sort of scientific-oriented school, and if you go to university and study physics, engineering, or chemistry, or so on, you get used to picture space-time, and it's not complicated at all to picture it in drawings, because what you do is to imagine you put on a line various photographs of the same of various rooms all at the same time. Okay, and then you put the set of picture of the same room a bit later, and then others a bit later. Okay, and then you have a big square of pictures where if you move this way, you have one room, another room, another room, another room. If you have this way, you have one room at some time, and then next time, next time, next time. So now we have a space-time. Each picture is one room at some time. So one axis is where, and one axis is when. And the entire collection of pictures is a space-time. So, and that's the kind of picture, the space-time pictures, that physicists draw all the time. They spend their time drawing pictures of space-time. And it's very easy, for instance, to use that if you want to describe how something moves, right? Because if you have this collection of pictures, and you suppose there was a guy walking from room to room, at the bottom level, the guy is here, and then the guy is next to next room, next room, next room, next room. So you have a curve in your space-time describing the motion. So physicists get very used to these space-time pictures, and then they say, oh, space-time is just a dimension. This was dimension of space, and that was a dimension of time. This answer your question, okay, how I picture it, but it does not answer your question, the second part of your question, which is, wait a moment, that's a picture. A picture is static.
Yes.
It doesn't tell me about the temporality. So once I go to that picture, it seems I've lost this, the sense that things are changing. Okay.
It's like taking a globe like the Earth and trying to represent it on a flat map. You can do it. You can represent it on a bit of paper, and it's good enough that you can use it for navigation and understand something about the world. But if you were actually trying to understand what the world really looked like and what it really was, then a map would probably give you quite a misleading idea.
That's very right. That's very correct. So a map is very useful and is a good picture of Europe or Asia. But it's misleading because the globe is round. It's not. When you map it down, you're killing one key aspect of the story, and that's a very good point. So when you draw this space-time diagram, so when you think of time as a dimension, you're killing one aspect of the story. I agree with you. What is this aspect? Well, this aspect, remarkably, it's complicated. It's not just in the fundamental simple equation of physics. It's not even in the geometry of this space and time. It is in the fact that the world around us, the past and the future, are very different. And this is the chapter of physics that talks about that is thermodynamics. In fact, the subtle point here is this extremely subtle point, is that think about the difference between the past and the future. Okay, for us it's totally obvious, right? The past has passed, we remember it, we know about it. The future, we don't know, it's open, we can choose. And then of course things happen in a certain way. They don't happen backward. If you break an egg, you see plenty of eggs broken, but you've never seen a broken egg coming back together. So there are things that happen in one direction but don't happen in the opposite direction. Now it turned out, and that's has been a major discovery of the 19th century, that every time there is this irreversibility, this fact that things happen in one direction, not in the other, there's always heat, temperature involved. When there's no heat, no temperature, the past and the future are equal. If you think, I don't know, think about the solar system. It's the sun and the earth goes around, okay? If you look it backward, well, there's the sun and the earth going around. There's nothing strange about it, right? There's no heat there. Or think of the pendulum. If you see a pendulum oscillating and you make a movie and show it backward, there's still a pendulum oscillating, okay? So where is the direction of time? But if you wait for a while and the pendulum slows down and stops by friction, right? And now make a movie and you look at backward, you see a pendulum start moving by itself. There's something strange here, okay? But the friction that slows down the clock produces heat, okay? So there is, or technically dissipation, energy that goes into heat, into work, or energy of the pendulum that is transformed by friction in a little bit of heat in the air or where the pendulum is attached. So every time there is dissipation, there's a distinction between past and future. So the difference between past and future, which is the root of our sense of flowing time, the root of the fact that we remember the past and not the future, and we can decide about the future but cannot decide of the past, has to do not with how things move, but with heat. And heat, temperature, that kind of thing, hot and cold, are very manifestation of the fact that there are very, very many things that move very fast. That's what heat is. So there are statistical phenomena. There are phenomena that involve a large number of molecules moving fast together, which means that our sense of flowing of time is not fundamental. Is not in the basic nature of things. Is in the approximation where we don't look at all the zillions of movement of the molecules. This is hard intuitively to digest. To me, this is one of the most surprising discoveries of modern physics. And I've spent a lot of time in my life to study that because it makes me extremely curious. So this very vivid, very intuitive sense that of the flow of time, it's actually a sort of artifact of the imprecise description of the world where we don't look at the microscopical details.
I find it very difficult to believe that this intuitive distinction that I have between the past and the present, which has a lot to do with something like memory. I know what happened. I know what we've just been talking about. I don't know what we're about to talk about. That seems to me a distinction in my mind that I can't quite explain. I can't quite get to grips with exactly why that's the case, but that seems to be one way that I understand the difference between the past and the future. And what you're telling me is that this actually just has to do with heat. I suppose I'm struggling to see exactly the link between. I understand that where we see irreversible science, where we see observations which don't work the same in reverse, heat is involved. I understand that. And so that tells us that the reversibility of time and heat have something to do with each other. But I still don't understand how it is that were it not for heat, let's say. I mean, you seem to be implying, and tell me if I'm wrong here, that if it were not for heat, if it were not for this law of thermodynamics, time would sort of be a nonsense concept. It wouldn't really be something that would exist or that we could at least understand. Does that mean that if there were no such thing as heat, that I wouldn't be able to remember the past, I would be able to remember the future, that distinction would break down? What would it look like if there were no heat, I mean to say?
Precisely so. It's exactly as you said. In fact, that has been one of the main themes of my work in the last 10 years. One of the papers which I'm more attached is Memory and Entropy, which is exactly about these kind of questions that you're referring to. So let me give you two points to answer this question here, very concretely. One is imagine that in a room, or maybe in the entire universe, everything dissipates, so you get to equilibrium. There's no more dissipation, no more friction, no more work becoming heat. So you isolate something and you wait until it has completely equilibrated. Now we're equilibrium. Okay. Totally. So it's not that there's a little piece there which still is out of equilibrium. It's that you equilibrate. Now, ask a question. Can you have memory there? And the answer is no. You cannot, because everything fluctuates around equilibrium. Given one moment of time, there's no way to remember something, because to have memory, to have a trace of the past, you need a mechanism, a physical mechanism that holds on in some way. I've spent time studying the physical mechanism of memory, and this memory requires dissipation, requires that there is some energy going lost into it. If the energy is already lost into it, you cannot have memory. Or in other words, if you look at a physical phenomenon with dissipation, you clearly see which one is the past and the future. As soon as it goes down to equilibrium, there is no phenomenology whatsoever that tells you which one the past direction, which one the future direction. Now, you may think intuitively, wait a moment, but if I was there,
yeah,
okay, suppose the universe has gone in total equilibrium. This is an idea by Boltzmann. Maybe in the future the universe completely equilibrate. There's nothing, just fluctuations, nothing anymore happening in a sense of in which a star is burning and biology is flourishing on Earth. Okay. Now you may think, well, if I was there, still there will be a past and future that passes. And the second point is that you're imagining a universe, okay, at equilibrium, and you there. But you, in order to think, your brain, in order to think, you need to dissipate. You need to be out of equilibrium. If your brain was in equilibrium, you're not thinking anymore, because thinking is remembering and doing a certain number of things. We think we eat, right? We have we ingest energy in food, chemical energy in food, and then we burn it and we dissipate it, and we use this energy, that non-dissipated energy, we call free energy in physics, that makes us to live and to produce phenomena which are time-oriented. We burn like a candle. A candle burns, is time-oriented, clearly. You don't unburn. You don't go back to making the candle from the air and the heat. So we are time-oriented. Our mind is time-oriented. This is why it's so hard for us to think in a non-time-oriented way, because our thinking is time-oriented. We think from past to future because our thinking is something that happened in our mind, which is a process, which is like a candle. It's burning, it's dissipating, it's very much oriented. So if in this completely completely thermalized at equilibrium universe, you were there with your actual brain dissipating, then it would not be really thermalized. If it would be really thermalized, your brain would also be thermalized and you were not thinking. And there would be truly no sense whatsoever to distinguish past and the future. The mistake we make is to take a correct phenomenology that we experience, which is a fact, and think that is a metaphysical universal thing. That's the mistake we make, right?
Yeah. Now, I mean, I understand that the dissipation of energy here is required for the mental processes involved in memory, let's say. That's certainly true. And yet it still seems strange to me that we've talked about whether that mental capacity, you have access to it or not, depends on whether energy is dissipating. If there's no energy dissipating, then your brain can't do things like that. Okay, but supposing that my brain can do something, energy is dissipating, my brain is doing something. If I look at the dimensions of space, the area to my left is just as accessible as the area to my right. I can reach out and grab either of them. And it would seem to me that we'd still need to live in a world that is not in equilibrium for me to be able to reach out to the left or reach out to the right. Everything you say would apply here too. If we were in complete equilibrium, then I wouldn't even have hands to reach left or right. And so there's a sense in which we need heat for me to be able to reach left and reach right. But once I've been given that ability, I can do both. And yet with time, once I've been given the ability to think, I can think about the past, but I can't think about the future. I can remember the past, but I can't remember the future. Why is that? Why is it that with every other dimension that we talk about, it seems like I can move in whatever direction I want and I can access whatever I want. But with time, there seems to be this arrow. It seems to go in one direction. Even if it goes at different speeds for different people, there's a sense in which one direction is accessible and one direction is not.
Well, first of all, it's not true that you can reach to your right and reach to your left, because what you can do is to send a hand to your right, but once your hand gets there, it's later in time. You have no access to the same moment to your right or to your left. Absolutely, you have no access. You should send something at infinite speed there. Wherever you send there, it takes time. So at most, you have access to something in the future a little bit to your right, something in the past a little bit to your right. In the future to your right. So it's true that you have access to some portion of space, but it's always in the future. Okay. Now, why you have access to this future possibility, but not to the access possibility? Because this accessibility you're referring to has to do with the thermodynamics in your brain. Once again, if you let's go to the opposite case. I mean, instead of everything thermalized, imagine there's no heat. There's only moving objects. Okay, so imagine a world. This is a different world I'm describing, in which there are only a few things. I don't know, solar system with the planets, but no air, nothing burning, just moving. Okay. If you look at it, you know the equation of motion, you know your physics. From the position of the objects and the velocity, you can find out with a calculation where they were in the past. But you equally can find it with a calculation where they will be in the future. So you have equal knowledge of the future and the past. Nothing makes a difference. So also in that case, there's no difference between the past and the future. Now you can say, well, what about if I make a measurement? You know, I look at something and then I write a piece of paper. What I've learned, I know it after, not before. Truly. But the actual process of measuring and writing a piece of paper is a dissipative process. It cannot happen in a world where there is no heat, no dissipation. So once again, you see, let me give you an analogy. You're telling me, oh, wait a minute. I mean, time is time. Time is passing. I mean, there are specific things which are so obviously connected to time that it should be very fundamental. Now, suppose you were telling me, oh, Carlo, I have big experience of light. I know that up is up and down is down. Okay. Of course. I mean, I throw something up, it comes down, and it's not the same. I always know where it's down and where it's up, and I can walk on the floor. I cannot walk on the ceiling. So up and down are profoundly different things. Okay. So it's inconceivable, a world without up and down. It's just in the nature of things that there is an up and down. Okay. And then I show you a picture of some astronauts in the capsule, okay, and fly away from the Earth. There's no up and down for them. Just all directions are the same. Things don't fall. If you put something there, it just stays there. And if they start talking to one another, and one says, "Where did you put the food?" It says, "I put it up." What do you mean? There's no up here. So they have an experience, and we know because our physics told us, but we even know because we saw this astronaut there. There's no up and down. And now you say, "Oh no, wait a minute, up and down are fundamental." And then a physicist can tell you, "No, look, they're not fundamental. It's just because here you're next to the Earth. The Earth is very big. There's attraction, so there's a great pull toward the down. So that's what you mean by down. It's perfect. It's true that there's an up and down here, but they're contingent, are an effect of the actual physical arrangement around us near on the surface of the big planet. So up and down are not universal issues, universal feature of the natural world, are perfectly well defined somewhere in some situation, and not defined at all, meaningless in other situation. And the passage of time, to our great surprise, because I do share this surprise enormous, I mean, it's a bit shocking, are like up and down. They are real, they're phenomena. There's a heavy phenomenology attached to the past and future, the difference in past and future, like difference up and down. And it's very vivid in our mind because we age. It's even attached to our deep emotions, right? We die. So it's a passage of time is not something emotionally neutral for us. It's something profoundly touching ourselves in our death. It's also what allows us to think. So in a sense, it's what makes us a thinking being. And it's very hard to believe that, like up and down, it's a contingent aspect of the way things are arranged in the world. It's not something that, according to our physics, if you're right, it's in the basic grammar of things. The world could very well be the same atoms of the world that make our world could be arranged in a different manner, where there wouldn't be this phenomenology of past and future, remembering, freedom of deciding, and so on and so forth.
At risk of sounding like I'm repeating a question, and tell me if you think that I am, hearing you talk about this world in which there's no heat, there are just objects moving around, everything's fully reversible. I understand that that's certainly true in terms of the mathematics, right? If you're describing the world, if you're using equations to describe the world, then everything's perfectly reversible until you try to take a measurement, in which case the very act of taking the measurement is something which dissipates energy and therefore isn't reversible. Okay, that's to do with like how we describe the world. Similarly, to the astronaut in the space station, they're describing the world in terms of up and down, and what we realize is that it's all relative, right? When they say up, they might mean relative to where their head and their feet is, but there's no actual up. They recognize that it's completely relative, and yet even to their relative up and down, which they would still distinguish from their own perspective, just as time is relative, but from your own perspective, it flows at a particular rate. The astronaut can still even if they can't instantaneously be up or down, it takes time, they can move up and they can move down. They can move in either of those directions. But with time, regardless of the question of whether we can run the equations in reverse, in terms of our actual experience, not only can we only move in one direction here, but we're sort of forced to move in one direction. It would be as if the astronaut was being forced to continually move upwards and didn't really understand why that was happening, and understood the concept of down, even if it was just relative to their own position, but for some reason was completely unable to move in that direction. And maybe they're moving up slightly faster than the person next to them, but they're all moving up, and they all can't help but move up, and they all can't move down. That seems to me a really strange state of affairs, but that's the situation that it appears we're in with time, right?
It is a strange set of affairs. And you have resorted to experience repeatedly. So the experience is correct. The experience is right. The question is, how do we understand this experience? The question is, can we understand this experience in terms of what we understand about the physical world? And if the answer was no, if the answer was, look, we have these equations that describe whatever they describe, and yet we have an experience that cannot be described, then I would agree with you. There's a problem here. There should be something else. But what I'm trying to say is that our equations do describe why there is this experience. They in a world where, like the one I describe, there should be a you that have exactly the experience that you have, even if somewhere else in the world there was no passing time. The subtle point here is how to interpret this experience. Is this experience, if the experience can be accounted by a world description, we shouldn't dismiss this world description because it makes this experience relative to us, or characteristic also of some subset of the universe. The analogy with up and down was that universal up and universal down, a common up, a common down, in our experience, while not in the experience of anybody who is outside, away from a big mass. So therefore, you can choose whatever you want to call it up, but it's meaningless. It's just an arbitrary definition. In a perfectly normalized universe, you can call it future and past, whatever you want. You can. Nobody forbids you. If you have a picture of that, you say, "Oh, I call this past, I call it universe," but it's meaningless because there's nothing really attached to that. And the idea, well, but that's inconceivable. It's a limitation of our capacity of conceiving, not else.
Why is it that objects of great mass have an effect on time? Why is it the case that if I were to go and orbit a black hole, time would move slower for me than it would for you back here on Earth?
Oh, yeah. Oh, yeah, very good question. Well, first of all, that's a key. That's a key insight of the general relativity, the theory that Einstein wrote in 1915, and it's a theory that tell us about gravity, about the pool, the gravitational pool, how it works once you look at its relativistic effects. And it's a remarkable theory because in 1915, Einstein wrote in 1915, and there was a couple of immediate success of the theory could explain, it could derive some peculiarity of the motion of Mercury and then the deflection of the light by the sun. So Einstein became pretty famous rapidly by his successes in his predictions, and also this was just after the Second World War, and it was very nice that this sort of German physicist, Germany lost the war, but there were some British physicists who could prove the German right. It sounded like we were all together, we all like each other, which didn't last long. But then general relativity went into a sort of sleeping mode for various decades, sort of respected, but a strange theory. Nobody took it very seriously because of the other predictions that the theory made seemed too far-fledged, seemed like delirious of a madman. And this other prediction that people didn't took very seriously were the expansion of the universe, the black holes, gravitational waves, all things that in the last, much more recently, in the last 10 or 20 years, have been confirmed exactly like were predicted by the theory. So nowadays, we are, in fact, the last few Nobel Prizes were all given to, prediction by Einstein realized. So we have a lot of confidence that this theory gives a good description of the world to some extent. Now, in what this theory, the great idea by Einstein that seemed to me work so well to describe the world is what we call the spatial relation like distances, the geometry of space. Okay, so the fact that the space in which we live is curved, like the surface of the Earth, so it's flat. So where geometry, Euclidean geometry works or doesn't work, and also the speed at which the clocks go, which, as we know now experimentally, it's affected by something. These geometrical things are not sort of fixed God-given structures of reality, but they are features of the gravitational field. So like there's an electric field or a magnetic field that, one of the antennas is capture for radio waves. You and I are communicating through radio waves, which are oscillation of electric and magnetic fields. So we know there are these fields. There's also a gravitational field. So it's sort of this entity which brings around the force of gravity. And this entity, it's in fact the thing that determines the distance and the speed of the clock. So in other words, what your meters and your clocks measure are features of the gravitational field, gravity. So there is a deep, this is an identity between gravity, namely what you make fall, you fall down, and the geometry of space and the geometry of time. They're really the same thing. So you can say, in fact, this has been said, if you read different textbooks in general relativity, they articulate this in different manners. Some say, oh, there's no gravity. It's just a space-time that is bended and curved. And some others, which I actually like better, say, oh, the geometry of space and what the clock measures is just features of gravity. Okay? Like, if you make the geometry of your ground around you, you're not doing abstract geometry, you're measuring the Earth. So if this round is, the Earth is round, there's a certain thing which is round. So the geometry of space-time, when we talk about the geometry of space-time, we go to school, they tell us Euclid geometry space is like, they're really talking about the gravitational field, okay? Which is an entity, like the electric field. And which has an entity, which is equation. Einstein wrote this equation and can move. These are the gravitational waves, can bend enormously like in black holes, and is such that it interacts with matter. So like the electric field interacts with charges. If you have a charged thing, you move it, you shake the electromagnetic field. So if you have a mass, you move it, you shake this gravitational field, which is space itself. And also a mass an electric charge create an electric field, generate an electric field. So a mass like the Earth create a gravitational field. The gravitational field is a slowing down of clocks. That's what it is. And in fact, unfortunately, the mathematics is a little bit complicated because I wish everybody could appreciate that. It's really spectacular. If you think this way, if you learn this way of thinking, okay, which, take a little bit of math and geometry and physics, but if you learn this way of thinking, you can do a calculation. So you have the Earth, this big ball of matter. So there's a gravitational field around, and this gravitational field is nothing else than the slowing of clocks, nothing else. Then you can do a calculation and ask, how would something move because the clocks are slowed? And you find exactly that it would fall down. So falling in simple set, let this fall down, okay, is to move in a space-time geometry where the clocks are slowed down. I have a very silly analogy. You run to the beach, you run into the water, and the water, your feet start sort of find the water, and so they have to slow down. So your full body falls in the water. Now it's a bit silly, but it's a bit like that. The reason you're falling down is because as time passes, you naturally move toward the mass.
Because your feet are moving slower.
Because your foot
once you get into the water. So the reason why things fall, the reason why anything falls, the reason why gravity exists is because time is moving slower at the bottom rather than the top.
That's correct. One can write this, can put that in absolutely precise equations. Namely, I can write a space-time. We were talking at the beginning about the space-time picture. We can write the space-time picture here, okay? And ask, okay, now there's this deformation because time goes faster up and slower down. And now I ask how a particle or body, a stone, could go from here to here in the most direct way. And the most direct way is to fall down. It's not to move straight, but is have this acceleration toward the down, which is what we call gravity.
That's fascinating. Most people think about this, and I certainly thought about it in this way before reading just a sentence that you wrote about this. They'll think that time slows down because of the effect of gravity. That's how we're often taught about general relativity. That was my understanding. It seems like you're suggesting it's not that time slows down because of gravity. Rather, gravity is the slowing down of time, and gravity exists because of the slowing down of time. It's almost like it's the other way around. That's
absolutely correct. That's absolutely correct. They're not two different things, one affecting one another. It's the same thing.
I mean, it's it seems like the more and more I learn about anything to do with relativity or gravity or time, there's always something new to blow my mind. And I guess it makes sense when the whole point of relativity is that these are essentially the same thing. It's all part of the same fabric. But put in those terms, thinking about the person running into the ocean and falling down because their feet are moving more slowly, and imagining that it's just like something like that going on globally, universally, as to why gravity has the effect that it has at all. I suppose conversations like this are helpful to begin to understand what people mean when they say things like, oh, time and space, they're just sort of the same thing. They're all part of the same fabric. Everybody knows that's the case. We learn that in school, but it's very difficult to conceive of it and conceptualize it. So it's been really great to have you here to help us picture that a little bit more clearly. Yeah,
the change of understanding of space and time that has happened thanks to the work of Einstein. Einstein's just the one who put together the various pieces and unlocked it. But then it's sort of the community as a whole that digested it, and then the experimental part that confirmed, that gave credibility of that. That's really a major change in our world picture. And I would say as big as the Copernican revolution, that has been enormous, has been has been a reshaping of the understanding of the physical, cosmological, and structure of the cosmos around us. If we think back at the Renaissance, the cosmological evolution, it's taking a century, maybe more, century and a half, to digest it through the work of intellectuals and then outside the people. So it's take time to digest that the way things are actually different than how people thought before. And I think we're going through a similar process. Einstein theory, it's actually profoundly verified, and it works so much better than the previous way of understanding things. It's a bit old because it's more over a century, but it's only in the last decades that has revealed all its power, even its technological power, right? I think everybody knows now that if we use the GPS and when we drive the car in downtown London or wherever we find the street, is thanks to the satellites that wouldn't work without general relativity. And so it's the technology now uses this because clocks up there, the satellites, our car has a little radio thing that communicate with the satellites, and clocks in the satellites go slower than down. If this wasn't taken into account, the entire system wouldn't work. So nowadays we have this great astrophysical confirmation of GR. We use it in technology. So as a civilization, we're getting confident that that's the best way of thinking about space and time and gravity. But also, we're more and more bringing it on that it's conceptually a spectacular revolution with respect to what we're thinking before. Time is something else that we thought. Present is something else that we thought. The now is something else that we thought. And the difference between the past and the future, which is what mostly we've been debating, it's surprisingly far less universal than what our intuition suggested.
Well, Carlo Rivelli, there's so much more to say, so much more to ask you about, but I must respect your time. The book, I suppose, that's most relevant to what we've been talking about today is The Order of Time, and I'll make sure there's a link available in the description. It's full of more illustrations, and I think there's some kind of anecdote in there. Isn't it true that when they first sent the satellites up into space and the scientists were saying, like, you need to understand that the time is going to run slightly slower, you have a bunch of sort of US military generals basically saying, that's the most ridiculous thing I've ever heard. And they ended up having to put a switch to turn on and off the compensation because the scientists said that they'll need it and the generals thought that they wouldn't.
That's exactly what happened. That's exactly what happened. The scientists told the engineers about that, and the engineers, of course, believed the scientists and said, okay, sure, we're going to do that. But when the project went up, GPS was run by the US military, of course, at the beginning. When the project went up to the general said, that's nonsense, let's not do it. So they ended up with putting the switch. And it was good because it was immediate, sort of vivid confirmation of the fact that you have to think this way, not the other way. Otherwise, things just don't work.
And who got it right? Was it the generals or the scientists? I'm only kidding. I'm only kidding. Carlo Rovelli, it's been great fun. Thank you so much for coming on Within Reason.
Thank you. This was remarkably nice. Thank you.
If you want to get